Welcome to The Explainer. Today, we're going to get into a really fundamental problem in computer science, one that's been a puzzle for decades. How in the world do you secure an operating system that, well, wasn't built to be secure from the get-go? It's this incredible story of clever engineering, big philosophical shifts, and really, the constant battle to keep our digital world safe. So, the heart of the issue is this thing called retrofitting security. And honestly, the best way to think about it is like this. Imagine a huge, fully built skyscraper, think Unix or Windows. Millions of people are inside, thousands of businesses are running. Now someone tells you, hey, we need to add a brand new bomb-proof foundation underneath it. But here's the catch, you can't tear the building down. You can't even stop people from using it. That is the scale of the engineering problem we're talking about, and it's a quest that has taken decades. And this whole problem really splits people into two camps, two completely different philosophies. On one side, you have the folks who say, let's just build a brand new, perfectly secure fortress from scratch. That's the security kernel idea. It's small, it's elegant, you can actually prove it's secure. But, and this is a huge but, it's often totally incompatible with all the software we already use. So then you have the other side, the retrofitters. They say, no, let's take the giant, popular castle that everyone's already living in and try to fortify it. You get to keep all your apps, which is great, but the complexity, oh, it's just off the charts. So here's how we're going to break this down. We're going to walk through this whole story, tracking how the ideas evolved over three big eras. This is going to be super helpful if you're studying this stuff because it gives you a really clean narrative for an essay or just to organize your notes. We'll look at the impossible problem, the first attempts, that microkernel dream, the big Unix comeback, and then we'll wrap it all up with the key things you absolutely need to remember. Okay, so what's the ultimate goal of this supposedly impossible task? Well, in theory, what you're trying to build is something called a reference monitor. And you really got to know this term. It is the absolute gold standard for security inside an OS. The easiest way to picture the reference monitor is as this perfect, all-powerful security guard. It stands at the gate between anyone trying to do something, that's a subject, and the thing they want to access, like a file, that's an object. Its job is to check every single request and give it a thumbs up or thumbs down. And for this guard to be perfect, it has to live by three golden rules, non-negotiable. Okay, pen and paper time, because this is huge for any exam. We've even got a mnemonic to lock it in your brain, CTV. Just think, can't trespass, verified. This stands for complete mediation, tamper-proofing, and verifiability. So what does that mean? 1, complete mediation. It has to check every single access, no exceptions. 2, tamper-proofing. Nobody, and I mean nobody, can mess with a guard. And 3, verifiability. The whole thing has to be simple enough that we can mathematically prove it's correct. Get those 3 down, and you've got the heart of the whole concept. So now you see why trying to slap this onto an existing OS is, well, just brutally hard. That first rule, complete mediation, good luck. You've got to find every single security-critical operation hidden in millions of lines of code. Tamper-proofing? You're up against things like dev/kmem in Unix. This is basically a backdoor that lets the super user directly reach in and fiddle with the OS's brain. How do you protect against that? And verifiability? Ha! Forget about it. You're not going to formally prove that millions of lines of C code are correct. It's just not going to happen. All right, let's jump in our time machine and go back to Era 1. How did the first engineers even try to tackle this beast? Well, their first ideas were pretty straightforward. They basically had 2 plans. Either try to slip a secure foundation underneath the OS that was already there, or just start bolting security features right on top of it. Yeah, a total rewrite just wasn't going to fly. So you had systems like Secure Xenix, and their whole approach was to take a bunch of great security ideas, many of them from the legendary Multics system, and just add them into Unix. The number one goal, though, was compatibility. Whatever they did, it had to keep the existing apps running. And this era gave us 2 really important ideas that are still with us today. First up, the trusted path. You know this one. When you hit Control-Alt-Delete on Windows to log in, that's a trusted path. It guarantees you're talking to the real operating system, not some sneaky program that's faking the login screen to steal your password. The second one is a bit of a mouthful, poly-instantiation, but it's a super clever trick. Imagine a top-secret user and a regular user both look inside the same folder. The system is smart enough to show them 2 different views of that folder, so the regular user never even sees that a secret file exists. No leaks. So this whole bolting things on approach, it was getting messy, really messy and complicated. So this led to a totally radical new idea, a new philosophy, really. People started saying, hey, what if the problem is just that the kernel is too big? If we can't secure a giant kernel, let's make it tiny. And just like that, we enter the age of the microkernel. The main idea here, which you see in systems like Mach, was to take the OS kernel and just gut it. Strip it down to the absolute bare minimum. All the stuff that's usually inside, like the file system, the networking code, they yanked it all out and turned them into separate programs called servers. The dream was that this super tiny kernel would be easy to verify, right? Just like those ideal security kernels. And then you could build your security features as servers on top of that solid, tiny foundation.
Now, this is another one of those key shifts you've got to know. The whole focus of security started to change. Before, everyone was obsessed with secrecy, making sure spies can't read the top secret files. But this era introduced a focus on integrity. It's a different problem. It's not about reading the file, it's about preventing unauthorized changes to the file. Think about it. You definitely don't want your web server, even if it's running as a trusted user, to suddenly be able to rewrite critical system files. That's an integrity problem. So we moved from just who can see what to who can change what. Of course, it wasn't that simple. There's always a catch, right? The kernel got smaller, sure, but the security problem didn't just disappear. It's sneaky. It just moved. Now, instead of one big kernel, you had all these little servers that needed to constantly talk to each other. And suddenly, securing the messages flying back and forth between them became the brand new giant headache. Okay, so the microkernel idea? Brilliant in theory. But in practice, it often had a pretty big performance hit. All that message passing slowed things down. So, for our third and final era, the pendulum swings back. The focus shifts back to good old Unix, the king of the server room. But this time, it's different. Now researchers had all these lessons from the first two eras, and they started combining them to build some really slick, sophisticated security. A great example of this is a system called IX. This thing was all about being flexible. Instead of just slapping a permanent top secret label on a file, it used dynamic labels. So if a not-so-secret program read a very secret file, the program's own security level would automatically float up. It also introduced these cool concepts of ceilings and floors, basically setting limits. You could say, this program can never become more secret than this, or its integrity can never drop below that. Super flexible. And this leads to one of my favorite concepts from this era, the assured pipeline. The name is perfect. It's exactly like a secure assembly line in a factory. You have process 1, which can only take its materials from the very beginning of the line. It does its thing, puts its finished part on the belt, and that part can only be picked up by process 2. Nobody else can touch it. And on it goes. It creates this beautiful high-integrity chain where you know for a fact that the final product at the end of the line is pure and hasn't been messed with. Then, building on these ideas, you get the DTE system. And this system went after the final boss of Unix security, the root user, the all-powerful God mode account. DTE's whole purpose was to finally tame root by applying the principle of least privilege. It put root processes into little sandboxes, or domains. So now, if your web server running as root got hacked, the attacker couldn't destroy the whole system. They were trapped in that one little domain. The damage was contained. A huge, huge step forward. Okay, let's zoom out and put this all together. We've been on quite a journey. This is the big picture, the stuff you really want to lock in for your revision, summarizing this whole evolution. So here it is, the 3-act story, perfect for any essay. Act 1, the commercial era. The philosophy, bolted on. The big innovation, the trusted path. Act 2, the microkernel era. The philosophy, shrink it down. The big innovation, a new focus on integrity with type enforcement. And Act 3, the Unix Renaissance. The philosophy, combine the best of both worlds. The big innovations, flexible tools like assured pipelines, and finally taming the root user with DT. And don't think this is just history. That type enforcement idea, that's the great-granddaddy of SE Linux, which protects Linux servers everywhere. And it's the core idea behind the sandboxing that keeps the apps on your phone from messing with each other. Which brings us to today. This whole incredible, decades-long quest has led to the relatively secure systems we use every single day. But that fundamental problem, that skyscraper, it's still there. And it leaves us with a really big question for the future. Are we going to keep patching and reinforcing the castles we already live in? Or is the next era going to be the one where we finally build those brand new, secure from the ground up fortresses? What do you think comes next?